How's it going? We are covering, let's see, we're doing today. We are doing acids, bases, and pH. This is a two-part series. This is going to be the first of two. The first one is going to be just acids and bases. So let's take a look here, and get started. Clean up my screen. All right, let's talk about it. All right, we talked about this before, but basically acids. So we talked about this during nomenclature and then briefly during chemical equations and chemical reactions. So I'm going to slightly change some stuff up here, right? So acids donate hydrogen ions and bases receive hydrogen ions. And we're going to call those, they can be called protons, right? So acids donate protons and bases receive protons. We talked about this before, but I said it had to be specifically in water. Well, we're changing the definition a bit. It's usually in water. Acid-base reactions usually occur in water. H1 pluses, H pluses are called protons. And when we say H1 plus or H plus, we're actually saying H3O plus. We kind of shortcut it and just to make our lives a little bit easier. All right. So let's follow this proton. This is a acid-base reaction, and yes, water can sometimes behave like an acid. And so if you look at these atoms here, these are the hydrogens. The white ones are the hydrogens. Just label a few of these. I guess I'll label all of them. But what's happening here is that this hydrogen is transferring to the NH3. So again, acids donate. So this H2O, this water, donated it to NH3, and NH3 received that hydrogen, and now it's bound to it. So that was the base, right? So the water was the acid, and the ammonia, or NH3, is the base. Again, because the acid gave the proton, NH3 received the proton, right? The reaction happened, and this is what they are after, right? That's ammonia is now an ammonium ion, and water is now an hydroxide ion because it lost the hydrogen or gave the hydrogen to the now the NH4 plus. All right. So these are kind of you can see similarities, right? Well, these similarities are their relationships, right? This acid, this water, lost or donated the proton to NH3. Now, that acid is now a conjugate base. After the reaction happened, see how this red and white and this water are almost the same, this hydroxide and water. The only thing missing is the hydrogen. So the conjugate base is what the acid turned into after it lost its proton, right? And so again, water gave up that, donated that proton to the NH3. The NH3 is the base, right? But after it picks up that hydrogen or that proton, it is now the conjugate acid, right? So these are paired up. And you can see the only difference between the conjugate base pairs is a hydrogen, right? This is NH3. It picked up the hydrogen, it's NH4, right? So again, acid will turn into the conjugate base after it's lost its hydrogen. A base will turn into the conjugate acid after it picked up a hydrogen, right? So these are called acid-base conjugate pairs, right? Here are a list of some common acids and bases. 6 strong acids: perchloric, hydrochloric. We named a bunch of these during the nomenclature lab. 6 strong bases. I want you to keep a look at something here. Most of them are hydroxide. But there's other ones. This is a very common one, sodium carbonate, CO3 2 minus, right? It can accept two protons, right? That can turn into H1 plus, H1 plus, and that can bond with those CO3 2 minus to create H2CO3, right? So that means this is a base, along with hydroxides, which most, like a lot of them are, maybe most of them are. Something cool about CO3 2 minus, right? It's amphoteric. So when it has a single hydrogen on it and it becomes CO3 minus, right? It could actually give up the hydrogen to water, or it could take a hydrogen from water or even something else. It doesn't really matter. Um, but HCO3 can pick up a hydrogen and it can donate a hydrogen. So it's called amphoteric. So it can accept or receive, accept or donate a proton. I guess we should say it can donate or accept, right? That would be a better way. Because accept and receive. We'll say it can donate or accept a proton, right? It's kind of cool. It does both. All right. When water's sitting around at 25 degrees, just kind of a little warmer than room temperature, what happens is water, some water, a very, very, very small amount of water gives up its hydrogen to another water, right? So this would be the acid and this would be the base. Actually, yeah, because it lost its hydrogen, right? And when it ionizes, the product, and it's only a very, very, very small amount. I think it's like 2 in a billion or something, like 2 in 1 billion. So the concentrations are very, very low. It's 1.10 to the negative 7th. That's a very, very, very small amount, right? But whatever water lost, same amount of water picked up that hydrogen, right? So then we have two values of K of 1.1, sorry, 1 times 10 to the negative 7, 1 times 10 to the negative 7. The Kw, which is the ion product constant of water, you don't really need to know the deep meaning of this, but we're going to use this a lot in this chapter. So basically, when you multiply the hydronium and hydroxide water, the hydronium, H3O plus, and the hydroxide ion concentrations together, we get the ion product of water, which is Kw, and that's going to be 1 times 10 to the negative 14th. Right? So we're going to use this number a lot when we're starting to calculate acids and bases and hydroxides and protons and stuff like that. All right, so we'll explore that a little more here. The ion product of water allows us to calculate the proton concentration or the hydroxide concentration if we know one of them, right? If we know one, we can calculate the other. If we know the other, we can calculate the first one, right? So this is how the Kw was calculated, right? The H plus and the OH minus. Again, brackets mean molarity. So we're tracking things in molarity. So moles per liter. Let me just write that up there. Just a refresher. If you need to go back and figure out what molarity is, go to the solutions chapter, and that'll be a good refresher. All right. So those two multiplied together are going to be 1.0 times 10 to the negative 14th. So we could use this equation, again, to calculate one if we know the other. You'll use this one if you know hydroxide concentration and you want to calculate H plus, right? You just do 1 times 10 to the negative 14th over the hydroxide concentration. And we'll use this equation on the right. If we know the hydrogen concentration or the proton concentration, I want to calculate hydroxide. So we do 1 times 10 to the negative 14th divided by H plus. All right, so we're going to go, and we actually know this number. Instead of 1, it should be 1.0 times 10 to the negative 14th. So that's what we'll be using. But this little table only shows 1. So just make sure you have a second significant digit on there. But we can go back and forth. If we know the hydrogen concentration, we just go to the right and we use this top equation. And that gives us the hydroxide concentration. If we know the hydroxide concentration and we want to know the hydrogen concentration, we go back this way and we just do 1 times 10 to the negative 14th divided by the hydroxide concentration. That gives us now our H plus concentration. All right. Well, let's try a couple. And I'll use my calculator on here so you can see what I'm doing. All right, let's take a look here. A solution of an acid in water has a hydronium ion concentration. So I'm going to just box this up with this so we can see what that is. Of 2.0 times 10 to the negative 6. What is the concentration of hydroxide ion? And concentration at 25 degrees C. All right, well, we know hydronium. We know this, right? So what we're going to do is going to get to. We're going to go this way. And because we're going this way, we're going to use this equation. All right, so this is going to be, I'm going to rewrite this. OH minus equals 1 times 10 to the negative 14 divided by the the hydronium or the H plus, right? So we're going to fill that in. We're basically just substituting one number. So it's going to be 1, oh, sorry, I messed that up. 1.0. So 1.0 times 10 to the negative 14 over 2.0 times 10 to the negative 6. And let's do it. So what I want to explain very well is that if you don't know how to use your calculator and you don't know really how to work exponents, you want to make sure that you're putting the in brackets. So what I mean is you want to put brackets around here. If you don't know how to use your calculator that well. If you do, you don't need to do that. It'll save you a few seconds of problem, right? But to be safe, we're going to keep those brackets on. So let's take a look here. Bracket 1.0 times 10 to the negative. And remember, your negative sign and minus sign are different. 14 divided by 2.0 times, again, brackets 2.0 times 10 to the negative 6. I'm going to push the arrow to get that over there. All right, so it's 5 times 10 to the negative 9. But we need two significant digits times 10 to the negative 9. And that is the hydroxide concentration. All right, let's take a look to make sure we did that right. There he is. I wrote it down actually. Cool. All right, looks good. So again, we're starting somewhere. Here we started. Here we're ending. It's similar to our little conversion table, right? Just follow the arrows, use the equation that's there for you. All right, let's do another one. What is the hydronium ion? We'll say H plus or H3O plus, right? In an aqueous solution with a hydroxide ion concentration, so 0.001 molar. And if you want to do exponential notation, let's take a look. 0.001. We're moving it 3 places, 1, 2, 3. So it's 1 times 10 to the negative 3rd molarity. You can use either one. These are exactly the same number. And if you need help with exponential and going back and forth, you can just review the capacity, right? Okay, so we are trying to find this. This is where we are starting. So we're just going to follow the arrow and we're going to use this equation. So it's going to be H plus equals 1 times 10 to the negative 14 divided by the hydroxide concentration. We know the hydroxide concentration here. Do that. 1 times 10 to the negative 14 divided by 1 times, oh, sorry, 1.0. Keep tripping up here. Right, 1.0, so we're 2 sig figs. This one is only 1 sig fig. So we have to make sure we take that into account. 1 times 10 to the negative third. Okay, let's try that. Let's put that in our calculator. Let's use a different calculator this time to get some practice at doing both. And so let's see, 1, and then again, brackets. So 1.0 times 10 to the negative 14. We're going to put use the arrow, closed parentheses, divided by, open parentheses, 1 times 10 to the negative third. Open or close parentheses, and we have 1 times 10 to the negative 11th. And that's molar hydrogen concentration, right? The brackets and molar are kind of redundant, but I'm just trying to show you, hey, this is what it actually means. I guess it's over there, so we don't need it. 1 times 10 to the negative 11th. All right, let's take a look. Okay, looks like I did that wrong. Oh no, sorry, I never put the right answer there, but I think we did it. All right, well, short chapter, just explaining pH, sorry, not pH, acids and bases, and we'll get into a little more detail on the next one. All right, that was it, and I'll catch you later.